Welcome back to MATA35. In the last half of class, we discussed classification of a number of different ordinary differential equations, as well as the difference between ordinary and partial differential equations. Now, today, in this part of the lecture, I'm going to talk about a very specific type of first-order ODE. We're going to talk about the pure time ODEs, as well as another type of ODE called separable ODEs, and we're going to give you an explanation of how to solve them. Now these will be the easiest to solve because they'll mostly just involve using integration. So let's go ahead and get started. What's a pure time ODE? So these, I'm only going to deal with the first order pure time ODEs, but second order ones also aren't too hard to solve because you can then just integrate twice. But here you can just solve your integration. So if y prime is equal to f of x, well then y is equal to f of x dx. And let's give a couple examples just to remind you all of integration. So if you have y prime is equal to 2x plus 5, then we know that y is equal to the integral of 2x plus 5 dx. And so y is equal to x squared plus 5x plus c. Let's see, we have another example, which is, let's say we had x dot is equal to sine t minus 1. So then x is equal to the integral of sine t minus 1 dt. And so x is equal to minus cosine t minus d plus c. And note that these here are both general solutions because we have these constants, and so they're actually an entire family of solutions. General solution. And that is one of the other facts about integration that we discussed somewhat, which is that we have a difference between general and particular solutions, which is that the general solution has some constants. Sometimes there are multiple constants, sometimes just one constant in it, and it covers all the different possible particular solutions. A particular solution then just assigns specific values to those constants. So, for example, if you had the example from the previous page, y prime is equal to 2x plus 5, and so y is equal to x squared plus 5x. Did I do that correct on the previous slide? Yes, I did. Okay, good. X squared plus 5x plus c. And this was a general solution. Well, we have several different particular solutions. So for example, y equal to x squared plus 5x plus 1. Well, that's a particular solution. Or y is equal to x squared plus 5x plus pi. Oh, what just happened? Plus pi. That's another particular solution. And of course, you have an entire family of these things. Now, one of the ways that you choose a particular solution out of the general solution is you have an initial value problem. So you specify initial conditions, so you choose a single particular solution out of the general solution. So let's use that example again. So if we have a general solution, y is equal to x squared plus 5x plus c, well then, if we give initial values, sometimes we'll call these IVs, and sometimes we'll call these an IVP. Let's say our initial value is y of 1 is equal to 10, where y is a function of x. So this you plug in for x, and this you plug in for y to solve for the constant. So this implies that 10 is equal to 1 plus 5 plus c, implies that c is equal to 4. So we get y is equal to x squared plus 5x plus 4 for our particular solution. Solution to initial value problem. Okay, so this is all pretty straightforward. Let's try it out. So what's the solution to the initial value problem? X dot is equal to sine t minus 1, where x of 0 is equal to 0. And let me reset the chat. Okay, so it looks like we've started getting some replies in. It looks like we had some B's, 1 or 2 D's. Well, let's see what happens when we solve this together. So we have x is equal to, well, when you take the integral of that, that's going to be minus cosine of t minus t plus c. Okay, so this here, this is the general solution. General solution. Oh, it looks like we're starting to get a couple of c's as well. So, let's see. A couple of c's. So that's our general solution. And now what we needed to do is plug this in, plug in for t, and plug in for x. So when you plug that in, you get 0 is equal to minus cosine of 0 minus 0 plus c. But now this is equal to 0 is equal to minus 1 plus c, so c is equal to 1. And so therefore x is equal to minus cosine t minus t plus 1, and this is our particular solution. And so the answer here was actually c, not b. And you have to remember that cosine of 0 is equal to 1, rather than just being equal to just being equal to 0. Okay, and one way that you should do is you should plug this in and check to see if it's true. And so if you then plug in 0, 0, what you'll find is that this is this makes this equation true, and so the answer was c in this particular case. So remember your derivatives, remember your integrals, and remember your trig functions. Okay, so let's move on. My PowerPoint is doing weird stuff right now. I apologize if I seem distracted. Something's weird about it. Okay, anyway. So, what else can we do? So there's another way we can think about these pure time ODEs. And it'll be a little bit odd to think about it this way, but it turns out that this will be helpful in solving other ODEs in a moment. So another way we can think about it is we can split the derivative by multiplying by dx, by multiplying in quotes, because dx is an infinitesimal, and we haven't talked about formally how you can manipulate them. But you can multiply by dx on both sides, and you get dy is equal to f of x dx, and then you integrate on both sides. Again, this is a little bit weird, but it is something that we can formally do this manipulation, and it'll turn out we'll get the same answer. So let's show this using the same example. So if we had y prime is equal to 2x plus 5, we can rewrite it. We rewrite it as dy dx is equal to 2x plus 5. And we have dy is equal to 2x plus 5 dx. If you take the integral of both sides, the integral of dy is equal to the integral of 2x plus 5 dx. And then what you get is you get y plus some constant, since when you take the integral you have some constant, is equal to x squared plus 5x plus some other constant. And you can rewrite this by combining the other two constants, x squared plus 5x plus c, because those all get lumped into the same thing, which is equal to c2 minus c1. So it's some other constant, and you get the same answer. Okay? So you might be wondering, why do we need to split this? Because you're just taking the integral of dy, which is just y, and we already knew that, right? The reason we do this is because what we can then do is, it turns out there are other equations that we can separate in the same sort of way that aren't just pure time ODEs. And this is an entire class of ODEs. We're only going to deal with first order, called separable ODEs. If we can split a first order ordinary differential equation so that one side has all of the dependent variable and the other side has all of the independent variable, then we can integrate on both sides. So let me give an example of this. So let's say we had 2y times y prime plus x is equal to 0. So now this here, this is a little bit hard to solve because this is, well, you might notice, this is nonlinear. It is not pure time because you have dependence on both y and y prime. It is not autonomous. So what can you do? Well, what we do is we split this apart. So this is 2y. We rewrite this as dy dx. And I'm going to rewrite this by moving the x onto the other side is equal to minus x. And then we multiply both sides by dx. So we have 2y dy is going to be equal to minus x dx. And then we can integrate both sides. Integral of 2y dy is equal to the integral of minus x dx. And so then you get y squared is equal to minus x squared over 2 plus c. And this is an implicit general solution. It's implicit because we haven't actually, so this defines y, but we haven't actually written out what y is. If you take another step, you take the square root of both sides, you get y is equal to plus or minus the square root of minus x squared over 2 plus c, and so this here is an explicit general solution. Now the reason we bring this up is because you can't always write an explicit general solution for a separable ODE, even though you will always be able to write an implicit general solution for that same separable ODE. So this is an important distinction, which is an explicit solution to an ODE with a dependent variable x and the independent variable x and a dependent variable y is of the form y is some function of x. So that's a standard solution. And so we had that example here. So if you had 2y, y prime plus x is equal to 0, and if we had some initial value problem, let's say y of 0 is equal to 1, then that would turn out to imply that y is equal to plus or minus the square root of minus x squared over 2 plus c. When you solve for that, that gives you y is equal to positive square root of minus x squared over 2 plus 1. Okay, so that is an explicit solution. You can't always do that, though. So an implicit solution to an ODE with independent variable x and dependent variable y is of the form some function of both f and y is equal to 0. And sometimes an implicit solution is the best we can do. And so I'm going to give an example of that. So if we have this example here, which is going to be y prime is equal to 2x divided by y plus e to the 5y. Okay, and let's say our initial values are y of 2 is equal to 0. Okay, so now this is pretty complicated, but we can rewrite this. dy dx is equal to 2x over y plus, keep on writing 5 first. That's e to the 5y. E to the 5y. We can rewrite this. So if we multiply both sides, we get y plus e to the 5y dy is equal to 2x dx. And therefore, when we integrate both sides, excuse me, when we integrate both sides, we get that y squared over 2 plus e to the 5y over 5 is equal to x squared plus c. And this here is an implicit general solution. Now, suppose we wanted to try to solve this IVP. Well, what we might do is we might have set x equal to 2, y equal to 0. And so then our IVP solution is going to have 0 over 2 plus 1 over 5 is equal to 4 plus c. So c is going to be equal to minus 19 over 5. And you get y squared over 2 plus e to the 5y over 5 is equal to x squared minus 19 over 5. And so this is an implicit solution, implicit particular solution. But note that it's actually really hard to directly solve for y in this case. And so often when I give you these separable ODEs, you can just leave the answer in implicit form, because if it's difficult to do explicitly. So one of the things that we need to now do is we need to figure out if things are separable or not. So again, this is going to be where I ask you to try things out. Let me reset the chat before we get going. Let's reset there. And so I'm going to ask, is this separable? Not separable. You cannot tell, question mark, or none of the above. Okay, so it looks like we're getting a bunch of answers. B. So people think this is not separable. Well, let's try separating it. So what do we have here? So we rewrite this. This is dy dx is equal to, I'm going to rewrite this by moving by adding y squared x sine x squared to both sides. And then what I'm going to do is I'm going to multiply both sides by dx. So this is, and I'm going to divide both sides by y squared. So d squared over y squared is equal to x sine x squared dx. So this is, in fact, separable. So one important thing to recognize is that it's not always easy to tell when something is separable or not. In this particular case, it was super hard to tell that it was separable until you actually tried it. Okay, let's give you another one. X dot x squared plus t squared e to the t is equal to 4. So is this separable or not? Let me reset, sorry, before you guys start replying. Okay, so let's see. Okay, so it looks like most people are saying A, though a couple people are saying B. Well, let's try separating it. So we have x squared times dx dt plus, I'm going to rewrite this and move the t's over to the other side. This is going to be equal to 4 minus t squared e to the t. And then I'm going to multiply both sides by dt, so then you have x squared dx is equal to 4 minus t squared e to the t dt. So yes, this is separable. Okay, so let's try another one. X dot t squared plus x squared e to the x is equal to 4. Is this separable or not? Now let's reset the chat. Okay. It looks like basically everyone's saying yes, it is separable. Well, let's see how it goes. I'll go ahead and say that the answer is yes, it is separable. And the reason for that is if you take dx dt t squared, move the, let's see, that's 4 minus x squared e to the x over to the other side, multiply both sides by dt and dt and divide out, so you end up getting dx over 4 minus x squared e to the x is equal to dt over t squared. So it is still separable. Okay, well, let's go again. Y prime is equal to xy. Is this separable? Let's see what people are replying. Okay, so most people think it's separable. A few people think it's not separable, and some people cannot tell. So it turns out this is separable. So you have dy dx is equal to xy, which gives you that dy divided by y is equal to x dx. And once you separate these things, you just have to integrate on both sides, and that will give you the answers, of course. Okay, let's try another one. What about y prime is equal to sine of xy? Let me reset before you guys type. Is this separable? Okay, so it looks like most people say no. And in fact, this is our only example here of one that isn't separable. In practice, most of them actually aren't separable, but it can look really complicated before and still be separable. And so you just have to try it out to see. So here dy dx is equal to sine of xy, and there isn't actually a way to separate the x and the y in the sign. So I have a question. What are you looking for to know that it is separable? Well, the answer to that is really just try to separate it. And if you can't separate it, then is there a general rule so we can simply eyeball it? Is there a general rule? Not really. One of the things that you might notice is just complicated expressions where you multiply together or have exponentials or sines or cosines with both an x and y in there. Those tend to not be separable. Sometimes they are, but those tend to not be separable. And other ones, Well, you just have to try it out. You just have to try to move everything to one side or the other side, and that's how you tell. Okay. Let's move on. So we have an example here where y prime is equal to xy. So let's use this example where y of 1 is equal to 1, and let's solve it. Let's solve it entirely. So we have dy dx is equal to xy. dy over y is equal to x dx. And so therefore, when you integrate both sides, what you end up with is natural log of the absolute value of y is equal to 1/2 x squared plus c. We have an initial value problem, so IVP, x equal to 1, y equal to 1. And so natural log of 1 is equal to 1/2 of plus c. So this is 0 is equal to 1/2 plus c, so c is equal to minus 1/2. And then you have natural log of y is equal to 1/2 x squared minus 1/2. And in fact, we can, if we take the exponential of both sides, you get y is equal to e to the 1/2 x squared minus 1/2. Yes, to answer your question, if you can get them on separate sides, then you're good. Yes, because then once you get them on two separate sides, then you can just take a single variable integral on each side, and then that gives you the final answer. Now, you won't always be able to get an explicit form, but certainly it'll give you an implicit form where you don't have any derivatives. And so that's the sort of point of like doing the separation. Okay, and for the last part of this part of lecture, we have a third part of lecture today, but for the last part of this part of lecture, let's have you all try it out. So remember, the first thing that you do is you need to separate onto all the x's onto one side and all the y's onto the other side, and then take the integral of both sides. And then I'm asking you, what is the answer? So I will go ahead and get you started while you guys are working on this. So this is just dy dx is equal to 3x squared e to the 2y. And so now the question is, can you separate this into the two different sides? Well, the answer is yes, or otherwise I wouldn't have given this to you as a problem. Get them on two different sides, and then you take an integral. In this particular case, to get them on two different sides, okay, we've started getting a couple of replies, but let's see what happens. So when we separate them, you get e to the minus 2y dy is equal to 3x squared dx. We're getting a large number of e's. Hopefully I didn't make, let's see, we're getting some a's and e's. A's, C's, E's. Okay, well, let's see what happens when we solve it. So you get e to the minus 2y dy is equal to 3x squared dx. You want to take the integral of both sides. Okay, we're getting some more replies. A's and E's. So then this here is equal to minus 1/2 e to the minus 2y is equal to... Wait, did I do something wrong? Oh, I did it wrong. Okay, so I guess the answer, so I made a mistake when I was writing up these answers, and so the answer is actually E, I think. But let me do it correctly and see what happens. So this here is going to be x cubed, yeah, plus c, and therefore what you get is, let's see, move that e to the minus 2y is equal to minus 2x cubed plus c. So minus 2y is equal to the natural log of minus 2x cubed plus c. And y is equal to minus 1/2 times natural log of minus 2x cubed plus c. And unfortunately, I made a mistake, and so the answer is actually none of the above. So I originally meant for this answer to be all of the above. So you'll notice that A, B, and C are actually all equivalent answers in this case. But unfortunately, I made a mistake when I was writing up my notes, and so the answer is actually none of the above. Okay, so having said that, let's take another 5-minute break while I switch slides, and then we can finish off with the lecture with linear first-order ODEs. So that'll be the last part of today's lecture. And we'll have a quick 5-minute break while I stop recording.